Hello and welcome to Mixer Design using CAD tool, which is NIAWR. We will continue with the design in this lecture. Next part, we want to design the RF LO isolation circuit. There are various options available. You can use coupling structures or you can use power combiners. Remember that the two ports of the power combiners are isolated from each other. Similarly, the two ports of coupling structures can be isolated to each other depending on which coupling structure you are going to use. In this particular case, we will use a simple power combiner as a RF LO isolator circuit. So, again schematics, right click, new schematic, RF LO isolator, create and go to elements, microstrip, power divider. You can see Wilkinson equal power split, chip resistor. You can select this, rotate, remember that Wilkinson power divider we have studied. So, these are the properties which can be entered from here as well, but the meaning you have to see from this window itself. So, W is the feeding line width at ports 1, 2 or 3, which should be 50 ohm characteristic impedance lines. So, I will set it to variable W 50. Width of branch lines, which is 50 root 2. So, I will set to W B. Length of the branch lines lambda by 4, I will set it to L quad, and R is 100 ohms because the system impedance is 50 ohms, which we will not change. The substrate is sub 1. Okay. Now, these variables we have to define. W 50 is equal to 2.38. Now, L quad should be equal to lambda by 4 at the LO frequency. The RF LO isolator has to be designed at LO frequency because LO power is quite high and which should be isolated from leaking into the RF and IF ports. So, we will make use of this tool again. Remember the impedance of the line is 70.7, the frequency is 3.75, the electrical length is 90 degrees, substrate details remain the same. Convert, you see that the width is 1.34 and the length is 14.8. So, L quad is 14.8 and WB is 1.34. L QUAD. Okay. Now, adding ports. Port 1 here, port 2 here and port 3 here. Okay. I will name these ports as RF, this is LO and this is RF plus LO. Okay. So, let us see the response of this particular circuit. I will create a new graph. I will say RF S param, RF LO isolator. Type is rectangular, create, add new measurements, select the circuit RF LO isolator, linear S parameters S11 in dB and S21 again in dB. So, apply 21, S11 apply. Now, the sweep frequency we have not specified, it is only 1 and 2 gigahertz as you can see, default project options. We will set it later. Click OK, go to options, project options, or rather than that go to the schematic, right click, options, uncheck it, uncheck the single point operation, and we want to see the operation from 3 to let us say 5.5 gigahertz. The step frequency of 0.05 gigahertz, apply, get 51 points, OK, and if I simulate, I get this response. So, as you can see, the notches are not at exactly 3.75 gigahertz, which is around here. So, we need to optimize the length. So, go to Isolator, add a tune tool, hit on L chord, go to the graph again, enable the tuner, and since we want to shift to a higher frequency, we will reduce the length slowly till we get now. Before that, let us analyze this. So, this is port 1, port 2. So, S11 is the return loss at port 1, S22 will be the return loss at port 2, S22 will be the return loss at port 2, and S21 is the isolation between port 1 and port 2. So, that is what we are looking at. I will hit the marker, I will check the frequency, which is 3.8 currently. I will have to, yeah, this looks pretty much good. I will freeze to this length. So, the isolation is around 48 dB and the return loss is also good at the RF port. So, this completes the design of RF LO isolator. Now, let us add these things together to make the mixer. New schematic, let us say mixer, add sub circuit. First, we will have the RF LO isolator, then I will go for the matching network, and then I will use the diode, which is diode bias. Okay. Now, at the RF and LO, we are going to add harmonic ports because we want to simulate the non-linear part of the device. So, go to ports, select harmonic balance, port 1 to be the RF port and port 2 should be the IF port. So, I will choose a normal port, small signal port for IF, and then I will choose harmonic port, which is port 3 for LO. Now, for this particular project mixer, again I have to set frequencies, go to options, uncheck this part, say single point and set the frequency to 4.25 gigahertz because that is the RF frequency. Double click on this, go to port and say tone 2 to have the frequency setting. So, if you see now the frequencies appeared over here, you can enter 3.75 gigahertz. The power is going to be varied. So, I set it to PLO equation. P underscore LO is equal to let us say 0 dBm initially, and this is my mixer circuit. This is the IF port, RF, LO, IF. I want to simulate this and I want to first check how does the output spectrum looks like. So, I will add graph IF out, add measurement, we have to go to non-linear, power, and we have to click on harmonic domain, frequency domain power, P harm. The circuit is mixer, we want to see the output at port 2, and sweep frequency should be 4.25 gigahertz, dB, apply, OK. If you simulate, you see this. This is our output of the mixer. Right click, add marker. If you see, this is at 0.5 gigahertz, which is our desired IF, and these are various spurious signals. Over these you see these are the leaking RF and LO signals. Now, the range is quite high. So, let me modify the axis limits, minimum for the left axis, let us say I keep it to -100 and max as let us say 30, apply OK. So, right now if you see, the power is -45 dBm at IF, which is quite low, and we are going to see the effect of LO power on the IF output. So, tune tool, tune the power, go to the graph, enable the tuner, minimum value is 0, maximum is let us say 20, and now if you see, if you vary the LO power, the IF power increases, which enables a higher conversion gain or lower conversion loss. We will study this with a sweep on LO power. Now, we will add the IF filter to remove all the spurious signals over here. For that, we will make use of a tool RF Sim 99. So, go to tools, design, filter, we will choose a Chebyshev filter, we want a band pass filter. First element is series, center frequency we require is 500 megahertz, the bandwidth is 100 megahertz. I will tell you how the bandwidth is chosen, number of poles 3, 0.1 dB ripple, calculate, you see that these are the values. Again go to schematic, new schematic, IF filter, create elements, lumped, inductor, closed form, capacitor, closed form. Now, these values of inductors are 82.1 nanohenry, this is 82.1 nanohenry, capacitor is 1.2 picofarad, 1.2 picofarad, copy paste, add the shunt arm, the inductance value is 2.8 nanohenry, capacitor is 36.5 pico, and these things have to repeat. Add ports, add graph, S param, filter, add measurement, go to linear, port parameters, S parameters, source IF filter, and S11 dB apply and S21 apply. Okay. Go to project, IF filter, right click, right click, options, uncheck this, uncheck this. We want to see the response from 0.1 to let us say 1.1 gigahertz, step to be 0.01, apply 101 points, simulate. You see, this is the filter response. If you add marker, this is at 0.5 gigahertz, you get an insertion loss of 0.1 dB around, and if you add another marker at 1 gigahertz, you see approximately 48 dB of attenuation is achieved at 1 gigahertz, which is required because if you see at the output of IF, this is the signal which is closest to IF, which is at 1 gigahertz. Okay, we want to remove this signal substantially. Okay, so this is my IF filter. I am going to add it to my mixer circuit. So I will stretch it. I will add sub circuit IF filter. Okay, I will add it to here. Save it. If I simulate again, I see the IF out. Now you see the IF signal is at 13.36 dBm, minus 13.36 dBm, and all the spurious signals have been removed substantially. Good. Now we will see the conversion performance. For that, let us go to the mixer. Let us add a sweep variable for the LO power starting from 0, stop 20, step size 4, okay, place it here, and let us keep the RF power at minus 10 dBm, save it. Now add new graph, conversion loss, create, add new measurement, go to non-linear, go to power, LSSM, large signal S parameter at harmonic, choose the circuit to be mixer, 2 port is port 2 IF port, from port is port 1, the harmonic is 0.5 at port 2 and harmonic is 4.25 at port 1, sweep frequency 4.25 and variable used for x axis. If I apply, OK, and I simulate again, I see that this is my conversion loss performance. If I add marker and I set it to maximum value, I see that the minimum conversion loss is obtained at LO power of 8 dBm. So this is the conversion loss performance of the designed mixes so far. You observe that at lower LO power levels, the conversion loss is very high. It decreases as the LO power is increased, and at an optimum LO power of 8 dBm, we get conversion loss of around 12.77 dB. If we further increase the LO power, the conversion loss degrades. Next, we will see the isolation performance. For that, we will create a new graph. We will use the same mixer circuit. We will say isolation, rectangular, create, add new measurement, non-linear, power, LSSNM, and in this case we want to see 2 is the RF port, which is port 1, from is the LO port, which is port 3. At port 1 we want to see what is the LO power. So the harmonic that needs to be chosen is 0, 1. So 3.75 gigahertz is the LO power, and at port 3 we should have the same harmonic, which is 3.75 gigahertz, and we sweep for different LO power levels. We apply. We also want to see the isolation between the IF port and the LO port. Apply. OK. If you simulate this, you see that The pink curve, which is LO-IF isolation, is quite good, which is greater than 90 dB, whereas the isolation between LO and RF port is greater than 10 dB and it attains its maximum value at, let us have a look, minimum, again 8 dBm LO power. So, again this is the optimum LO power for maximum isolation between LO and RF port. Again, these are large signal simulations. It is important that we simulate it using large signal analysis. Next, we will move to noise figure. For that, we have to create a noise figure test bench. So, go to schematic, right click, new schematic, noise figure test bench. And in this case, I will use the entire mixer circuit as a sub circuit. It is better that we name the ports so that we do not connect ports wrongly. So, port 1 is RF, I will name this port as RF. Okay. Port 3 is LO, name this as LO, and port 2 is IF, will name this as IF. Okay. So, in the NF test bench, now if you see RF, LO and IF. For noise figure simulation, the RF port is treated as a small signal port. So, you connect a simple small signal port to the RF. LO is considered as a large signal port. So, we use harmonic port for LO. So, I will just copy this port and paste it here. IF is again a small signal port. Okay. Now, for noise figure analysis, we need to add a component. Go to elements, go to measuring devices, controls, and if you drag this, see the component NL noise. We have to add this noise component for noise figure analysis. So, port 2 is port 2, which is the IF port. Port from is port 1, which is RF port. So, noise is being added from RF to IF, which is correct. Now, we have to set appropriate values of NF start and NF end, and these values will correspond to the RF bandwidth. Let us say the RF signal centered at 4.25 gigahertz has a bandwidth of around 100 megahertz. So, the IF ranges from 0.45 gigahertz to 0.55 gigahertz. So, NF start I will set it to 0.45 and NF end I will set it to 0.55, and steps I will use 10 steps. Now, once this is done, we have to define the PLO. So, add equation PLO equal to 0, and we will set a sweep from 0 till 20, step of 4 for the LO power level. Now, to view noise figure, we will create a new graph of rectangular type. And if test bench, you have to set this to tone 1, okay, and in the project options, uncheck the default, set to single point and set the frequency as 3.75, hit OK. Now, if you go here, add new measurement, choose NF test bench, noise figure SSP, and you see that now the source is NF test bench, output large signal harmonic which is 0, input large signal harmonic as 1, upper you have to uncheck this, sweep frequency you have to set to 3.75 gigahertz and use x axis as the sweeping LO power level. If you apply OK and if you simulate, you get this performance for noise figure. So, this is the noise figure performance against various LO power levels. We will add marker and we will check the minimum noise figure, which is 5.9 dB and which happens to be at the same LO power at which we get best isolation and best conversion loss. So, it is the LO power of 8 dBm that gives us minimum noise figure, maximum isolation and minimum conversion loss. So, this is our final mixer circuit. We have an RF LO isolator circuit where LO and RF are applied. We have RF input matching network. This is our diode which is biased at appropriate biasing point, and after that we have an IF filter to reduce the spurious response and to filter only the IF frequency from port 1 to port 2. At port 2 we observe the IF output. Okay. So, we completed the mixer design and in the notes we can add the performance. So, conversion loss was around 12.7 dB. We had LO RF isolation equal to around 20 dB, LO IF isolation of around 90 dB, and we got a noise figure of around 6 dB, and all these things are obtained at LO power level of 8 dBm. So, this completes our design of a single diode mixer using a CAD tool, which is National Instruments AWR design platform. We studied how to model the diode, how to bias the diode, how to design different passive circuits like Wilkinson power divider, or you can use coupler as well. We studied how to design a matching network using this tool. We studied how to design the IF filter and how to combine all these components into the final circuit, and then we also studied how to use the simulation parameters to study various performances, which is conversion loss performance, noise figure performance or isolation performance. With this we will stop here. Thank you.